Hi everyone. Today we're going to look at some review questions I sent out to review the other day, and I gave you some answers. We're going to go over some of that. So let me share the screen with you. And so we have some things to consider here. First off, you should know if you have a set of ordered pairs, how to determine if it's a function. You should be able to determine the domain and the range of that set. You should also be able to determine if something is one-to-one. So let's first answer the first question, is this a function? So for it to be a function, every x has to only have paired up with one y. And so 1 is only paired up with 2. The x value of minus 3 is only paired up with 5. The x value of 7 is only paired up with minus 8. The x value of 2 is only paired up with 3. And the x value of minus 7 is only paired up, minus 5 is only paired up with 7. So it is a function. The domain would be all the x values, 1, minus 3, minus 7, 2, and minus 5. The range is all the y values, 2, 5, minus 8, 3, and 7. Is this one-to-one? That's not on here, but we should be able to answer that. So to be one-to-one, we first determine it's a function from x to y. Then is it a function going back from y to x? Well, let's take a look. 7 is paired up with minus 5. And that's the y value of 7. There's no other y value of 7 paired up with anything else. 3 is paired up with 2, the y value of 3. There's no other y value of 3 paired up with anything else. The y value of minus 8 is paired up with 7. There's no other y value of minus 8 paired up with anything but 7. 5 is paired up with minus 3, and only minus 3. So the y value of 5 is only paired up with minus 3. And the y value of 2 is only paired up with 1. So it's a function both ways. You should also know how to do the one-to-one test for horizontal one-to-one test. You have a graph. Any horizontal line crosses the function more than once, it is not one-to-one. If it crosses the graph only once everywhere, then it is one-to-one. You should know how the parent functions, the basic parent functions. I'm not going to list them here as far as a picture, but you should know what a linear function looks like. You should know what the parent function for a quadratic looks like, for an absolute value, for a cubic. You should know what the parent function looks like for a square root function, and a function that is a cube root. You should also know what the parent function looks like for a reciprocal function of 1 over x. You should be able to determine what happens to the parent function. Is it compressed, stretched? Does it move left, right? So on and so forth. So in this case, we have a minus 2/3 f of x plus 3 minus 4. So the x plus 3, it says it's x plus 3, it moves it left 3 units. If it was x minus 3, it move it right 3 units. Since we have a 4 and it's a negative 4, it moves everything down. Since we have a negative in front of everything, it reflects about the x-axis, everything's turned upside down. And the 2/3 is less than 1, so that means it compresses the function, it makes it wider. Okay? Stretching, when it's greater than 1, makes it narrower. You should know how to do composite functions. We have an example of two composite functions. F comp g of x is a. So that means every place in f, we're going to put g of x. So since f is the cube root of x minus 7, we replace the x with x squared minus 6. So we end up with a cube root of x squared minus 6 minus 7. Simplifying, we get x squared minus 13. The next one, g comp f of x. This means every place in g where there's an x, we're going to put the cube root of x minus 7. So g of x started out as x squared minus 6. So where the x squared is, I replace that x with the cube root of x minus 7. And I still square it because the x was squared, and minus 6. There really isn't any simplifying we can do here. So that's our final answer. For 6, f of x is equal to 4x squared minus 3. Whoops, went a little too far there. Sorry about that. And so find f inverse of x. Now we have to limit the domain to where x is greater than or equal to 0, or else it won't be one-to-one. So in this case, the first thing we do is we change the f of x notation to y. Then we exchange the x's and y's. So every x becomes a y and every y becomes an x. So we have x equals 4y squared minus 3. And then we solve. The way we solve this is we'd add 3 to both sides, divide both sides by 4, and then square root both sides. We don't have to worry about the minus square root because we can't have a negative value here. Okay. And so we end up with f inverse of x equals x is greater than or equal to minus 3. Why? Because x, anything less than minus 3 would make a negative underneath the square root. And then we take a look at for f of x equals minus 3x squared plus 4x plus 4. The first thing we're going to do is we're going to find the vertex here for this. So x is equal to minus b over 2a at the vertex. So b is 4, a is minus 3. So we actually have minus minus. I forgot the minus there. Sorry about that. Let's put that in there. There we go. And let's put it in parentheses. So you might want to make that note as well. Sorry about that. Oops, that's the wrong way. There we go. That's better. And we get a positive 2/3 for the vertex. So to plug that in, how you evaluate this, I don't care. You could do it with your calculator. You can do it by hand. We plug in 2/3 for x, and we find out what y is. In this case, it ends up being 16/3. So the vertex at 2/3, 16/3. To find the x-intercepts, we set the function equal to 0. Okay. I'm going to factor out the minus. Okay. Why? Because it's easier to use both the quadratic formula and factoring, whichever you want to use here, if the leading term is positive, and you get the same roots either way, the same zeros. I'm going to multiply both sides by minus 1 to get rid of the negative, and then factor. So that gives us 0 equals the quantity 3x plus 2 times the quantity x minus 2. So this gives us zeros at x equal minus 2/3 and x equal 2. To find the y-intercept, we let f equal or x equals 0 and find f of 0, we get 4. And so to graph, my graph didn't show up as well as I wanted it to. We have a x-intercept at minus 2/3, another one at 2. We have a y-intercept at 4, and the vertex is at 2/3, and then what was it, 16/3. Okay. And our end behavior is going down because we have a negative leading term. Now, whenever you see a problem where it says find the average rate of increase or decrease, you're really looking at the slope of a line. So when we look at this, it says 1970, the supply of a certain type of candy bar is 1.3 million bars in 2000. In 2000, the same supply of candy bar was 11.7 million. What was the average yearly increase in this type of candy bar from 1970 to 2000? So first we're going to let 1970 be the start year. We'll let it be year equals 0. So that means that 2000 is 30. That'd be 30 years after 1970. This gives us the data points 0, 1.3, and 30, 11.7. Now find the slope of this line that connects these 2 points. So m equals the difference in y's divided by the difference in x's. So I decided to start out with 11.7 in the numerator. Okay. And I subtracted the 1.3, which means I have to start with a 30 down here and subtract the 0. So that gives us 10.4 over 30, which is about equal to 0.35. Now, it's just as important to be able to interpret what that average rate of change means. So the interpretation is this. The average increase in the supply of a certain candy bar between 1970 and 2000 was about 0.35 million per year. Know how to find the bottom line of best fit on your calculator? That's that ln-reg information. Putting the x's into list 1, the y's into list 2, and using the ln-reg feature of your calculator will give you this a and b. A is the approximate slope of the best fit line, and b is the y-intercept. In 9, we have a function that's already a polynomial that's already factored. And it tells us that we have zeros coming from x plus 2, x plus 1, and x minus 3. Okay. First, the first factor is degree 1, the x plus 2. The second factor is degree 1, the x plus 1. And the third is degree 2 because it's quantity squared. So first times a 2 gives us a polynomial of degree 4. The zeros are minus 2, minus 1, and 3. And those we can find by setting each factor equal to 0 and solving for x. So 3 is just a repeated factor, since it's a multiplicity or a degree of 2. For the multiplicity, minus 2 and minus 1 are 1. Okay? And 3 has a multiplicity of 2. We kind of covered that already with respect to the part A. In part A, don't forget, it said what is the degree of the polynomial. So we figured out the degree of each factor. So the degree of each factor really is a multiplicity of that factor. And what's the end behavior? Since we have a negative leading term, it goes down in both directions toward negative infinity. And as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. Okay? So y goes to negative infinity in both cases, and that's consistent with a fourth degree polynomial with negative end behavior. Draw a possible graph of this function. Again, this could be basically, could look any place in between the zeros. However, you have to have the end behavior that represents a negative leading term for a fourth degree polynomial. You have to have minus 2 and minus 1 representing zeros where the graph goes through the x-axis because each one of those has degree 1. And at 3, you have to have the graph just touch and then go back down because the degree there is 2. Remember, when the degree is even, the intercept the graph just touches the intercept. It doesn't cut through it. So for x cubed plus 4x plus x minus 6, I want you to note that I changed this. I realized I copied and pasted the wrong function here. I apologize for this. This is the correct one. So the p's are all the factors for minus 6. Those would be plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. Q is all the factors for the 1 in front of x cubed. So that's just plus and minus 1. So the p over q's are just all these p's that we have divided by 1. So we have plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, and plus and minus 6. We can find all the zeros with the aid of our calculator, again, either by doing the table set or in entering each x one at a time, or just calculating it out one at a time on our calculator without the table set, just from our home screen. Either way, f of 1 equals 0, f of minus 2 equals 0, and f of minus 3 equals 0. So those are our 3 zeros. We have no more zeros than those. How do I know that? Because it's a cubic. A cubic will have at most 3 real valued zeros. Okay? Doesn't have to, but at most. None are repeated, since we have 3. And here is the synthetic division for each one. So let's go through just to review some synthetic division. These are the coefficients for the polynomial. 1, because that was the x cubed. 4 was the x squared part. 1 was the x, and minus 6 was the constant. And we're dividing by 1 because that's one of our zeros. So we drop the leading term straight down and multiply this by 1. 1 times 1 is 1. Put it in the next column. We add these together and get 5. Then we take our zero, our possible 0, multiply by that 5. 5 times 1 is 5. Put it here. 1 plus 5 is 6. Then take the 1, multiply it by the 6. Add it here. Minus 6 plus 6 is 0. So that tells us that we actually have a 0 there. No remainder. So it divides out. So it's a root. And so when we look at this, let's pay attention here. This 1, 5, and 6, that's actually x squared plus 5x plus 6 now. Okay? I could go back and try to factor that and verify the rest, but since we're doing synthetic division, we might as well. Let's look at the 2. Drop the leading term straight down. multiply by minus 2. Minus 2 times 1 is minus 2. 4 plus minus 2 is 2. Take the minus 2, multiply by our answer there. Minus 2 times 2 is minus 4. 1 minus 4 is minus 3. Take our minus 2, multiply by minus 3, put it here as 6. Minus 6 and 6 are 0. So that tells us there's no remainder, so it's a 0. And then the last one here, minus 3. Drop the leading term down. Minus 3 times 1, minus 3. Put it here. 4 minus 3 is 1. Minus 3 times 1 is minus 3. Put it here. 1 minus 3 is minus 2. Minus 3 times minus 2 is 6. Put it here. Minus 6 plus 6 is 0. So no remainder. So that verifies, since there's no remainder in each of those cases, that it's a 0. Write in factored form. So we're going to take f of x and write it as x plus or minus each root. If the root is negative, if the 0 is negative, we put a plus in front of it when we put it in factored form. If the 0 is positive, we put a minus in front of this in factored form. Remember, in factored form, it has to be the opposite sign of the 0. So minus 3 was one of our zeros. So that means we make it x plus 3 in factored form. Minus 2 was another one of our zeros. So that means we put in an x plus 2 in factored form. And then x minus 1 comes from the x equal 1. Again, we put an opposite sign in factored form. So now we're going to graph. Okay. We're going to graph each one of the, we're going to graph this rather. So, and then we're going to approximate local mins and maxes. Now remember, local mins and maxes are the high point would be a local min, low point would be a local max. Each place there's a turning point, there could be a local max or min. Okay? So the graph of the calculator, graph with the calculator, make sure the intercepts and turning points are on the screen. Use the calc key to find the local extrema. For the min, select 3 on the calc menu. The calc menu is a second function for window. Set a left bound, that'd be over here, and a right bound. Move your cursor over here so that that low point is someplace in between. Then hit enter, enter, and enter. And it yields an x value of minus 0.13. So that's our minimum. For the max, we're going to do basically the same thing, except we're going to choose 4 on the calc menu. Set the left boundary. The left boundary would be to the left of that high point. The right boundary would be to the right of that low point, or high point rather. And then hit enter, 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 and we get 2.535. Okay. And then for F, you should be able to do a problem like that where I give you a polynomial and then write the answer into that polynomial form plus the remainder over what you divided with. You should know how to find an absolute max and min. The absolute max and min. The absolute max and min can occur if you have a closed and bounded function. So if I have a function that ends here and ends here, ends on the x-axis someplace, here and here, in between any high point or low point would be an absolute max or min. Okay? You should be able to graph a piecewise function, and I sent you that out, the solution to this out. You should read that over and know how to do that. If you can do these problems, for the most part, you shouldn't have any problem on your test. Okay? Your test is due, I believe, sometime between now and the 2nd. Hopefully this helps you out a little bit. Have a good day.